So, as part of this supplemental Chapter 7 model kit exercise, we're going to be looking at alkene addition reactions and the stereochemical outcome of alkene addition reactions. The three major alkene addition reaction pathways are the cyclic ring forming pathway, which yields a syn stereochemical outcome, the concerted addition pathway, which also yields the syn addition product. And the third major alkene addition reaction pathway is a ring formation, ring opening pathway, which yields an anti-stereochemical product. So as part of this exercise, we're going to be looking at the stereochemical outcome of each of these reaction pathways for these various alkene addition reactions using both dash wedge depictions, looking at it using a model kit, and also looking at these alkene addition reactions using some Newman projection perspectives. So let's look at the first reaction pathway, which focuses on a cyclic or ring-forming alkene addition reaction pathway. A classic example of this is epoxidation with peroxy acid, such as metachloroperoxybenzoic acid. In this case, we're going to look at the stereochemical outcome for these reactions for both E and Z alkenes. So let's start with the E alkene. So first and foremost, in these kinds of cyclic ring-forming alkene addition reactions, they typically occur via a concerted mechanism where the group, in this case the oxygen atom that's going to be installed, is installed syn, as in both of the formed bonds to this oxygen atom are going to be on the same face of this molecule. You can't really have a trans three-membered ring. It's too strained. So for a lot of these cyclic ring-forming alkene addition reactions, the ultimate stereochemical outcome is going to be a syn stereochemical outcome. So just drawing out this mechanism, let's add in our lone pairs. So in this case, we end up with a concerted pathway. This is the typical epoxidation mechanism, where we have attack of the electrophilic oxygen atom by the alkene. We observe breaking of this peroxide oxygen-oxygen bond, and the hydrogen and the oxygen-hydrogen bond is broken as these pi electrons are used to form a new oxygen-hydrogen bond. This entire sequence of bond forming and bond breaking steps occurs in a concerted single step. The net result is we'll install this peroxide oxygen atom, will generate an epoxide. And in this case, the oxygen atom and the two newly formed carbon-oxygen bonds will be syn to one another. Let's take a look at this reaction using a model kit now. So here is a model that I've prepared, and I've used a set of special atom labels in making this model, in that the alkene carbons here, let me set this up so that it's in the prepared view. These alkene carbons are special carbons from your model kit that have additional pegs. This is really useful in the model kit because it allows us to show the bond forming step, and it makes it very easy to track bond forming and bond breaking, especially when you have inversions at a stereocenter. So here's our alkene that we've made using our model kit. You're going to want to use the special carbons, which have 6 pegs instead of 4 for your model kit. Now, in terms of epoxidation, the net result is we're going to be installing this oxygen atom on the same face of the molecule. So the net result of this epoxidation reaction is we'll form 2 new carbon-oxygen bonds, like so. And in turn, we break one of our alkene carbon-carbon bonds. So this gives us the following rough depiction using our model kit. As we can see, the epoxide oxygen, the carbon-oxygen bonds are syn. And as you can see, since we started with an E-alkene, the two methyl groups are on opposite sides, on opposite faces of our molecule. If we were to look at this from another perspective, as we can see very clearly, let me just staple this in to make it easier for you to see the stereochemistry. This methyl group is pointing towards us, while this second methyl group on the second carbon is pointing away from us. So let's just draw that alternative depiction. So as we can see, if we start with an E-alkene, where both the methyl groups are on opposite sides of the alkene double bond, when you run this epoxidation reaction, the epoxide oxygen is installed syn, and as a result, the two methyl groups end up, because we have an E-alkene, these two methyl groups, these two alkyl groups are trans to one another. They're on opposite faces of our molecule. Let's look at what happens when we have a Z-alkene. Same general mechanism. However, in this case, because both the methyl groups in this Z-alkene are on the same side of the alkene, they're cis to one another. In our product, when the epoxide oxygen is installed, both of the methyl groups end up on the same face. Let's take a look at this using our model kit now. So let's now make a model. We're going to have to modify the original model that we made because we need our methyl groups to be cis to one another in the Z-alkene. So let's just move our methyl groups over. And now let's take a look at our model. So here's the model of the Z-alkene. Now we're going to install the oxygen atom. The oxygen atom is installed on the same face. And as we can see in our product, looking at this epoxide, the methyl groups are cis to one another. If we start with a Z-alkene, where the methyl groups are on the same side of the alkene, in the product epoxide, we in turn observe the methyl groups to be cis to one another. As we can see from this front-on perspective, the methyl groups are wedged, the hydrogens are dashed. The methyl groups are pointing out towards us. Now, of course, there is an alternative product that can occur if epoxidation occurs from the bottom face. That's why we typically put plus enantiomer. This particular compound is a unique case because it has an axis of symmetry and is a meso compound. This is something that can happen when you have symmetrical alkenes. But just to note, the other product, which is usually unique, occurs if the epoxidation reaction occurs from the bottom face, and thus the epoxide's installed on the bottom face. Okay, so as we can see using our model kit, we are able to better understand the stereochemical outcome of these alkene addition reactions for this cyclic ring forming pathway. Other reactions that follow these cyclic ring-forming alkene addition reaction pathways are epoxidation and cyclopropanation. So just to make sure that we understand what's happening here, let's try to predict the product of the following reaction. In this case, we have this alkene reacting with diiodomethane and a zinc copper complex. These are textbook cyclopropanation conditions. So take a few moments and try to predict the product from this reaction, and we'll discuss momentarily. Okay, so first and foremost, we're going to make the carbene, which looks like this. Carbene addition occurs in a concerted manner where both of the newly formed carbon-carbon bonds are formed syn to one another on the same face. In this case, we have the E alkene, and as a result, after cyclopropanation, the two methyl groups, because they're on opposite sides of the alkene, the two methyl groups in the final product end up on opposite sides, opposite faces. You also observe the enantiomer, which occurs if cyclopropanation occurs from the bottom face. To show you what that looks like, it looks like this. Okay, so we talked about the first reaction pathway, which focuses on ring forming or the cyclic pathway. Let's take a look at some other alkene addition reaction pathways. And before we look at the next reaction pathway, let's talk a little bit about an alternative way that we can help visualize these alkene addition reactions. And this is done via the Newman projection perspective. So in order for you to best see how to draw a Newman projection for these alkenes, let's break out the model kit. So here is a textbook E alkene. And if we wanted to take a look at the Newman projection, if we wanted to look down one of these carbon-carbon bonds, all we have to do is rotate our molecule and look down one of our carbons. So in this case, if we're drawing out our Newman projection, we see we have this front carbon in the front, we have a methyl group on the right in the front, a hydrogen on the left, and in the back, the methyl group's on the left and the hydrogen's on the right. So let's try to draw that Newman projection now. So in this case, we have the methyl group on our front carbon on the right, the hydrogen on the left, and in the back, we have a hydrogen on the right and a methyl group on the left. Now, why is this useful? Well, when you have this Newman projection perspective, it gives you a very quick route to draw molecules and draw the stereochemical outcome of reactions without having to go through as many steps or abstractions. The Newman projection view can also help you notice things related to strain in the transition state and some other aspects of the reaction that can best be seen from this perspective. The nice thing as well is for the Z alkene, the only thing that changes in our Newman projection is the fact that the methyl groups are now both on the same side. So now that we have this initial Newman projection view of our alkene, let's see how we can apply that Newman projection view to help understand reactions. So let's take a look at this next case, and let's take a look at our same epoxidation reactions, but this time from a Newman projection perspective. So looking at our E alkene, as we've already previously established, we have the methyl group on the right in the front, hydrogen on the left. And then in the back, we have the hydrogen on the right and the methyl group on the left. To show that this is true, here's our model, here's our Newman projection view. As we can see, the front methyl group's on the right, the back methyl group's on the left. Now, when we look at the epoxidation reaction, the oxygen atom is going to be installed on the same face, like so. And we can draw that from our Newman projection perspective. So we can put the oxygen on the top face. Here's what that looks like so. Let's show you now what this looks like on our Newman projection drawing. So we're forming a new bond to the oxygen atom on our front and back carbons. This in turn gives us the following Newman projection after we form our desired carbon-carbon bonds. Now, I do want you to note one quirk of these cyclic reactions that's pretty interesting is that the product, because it's a three-membered ring, the substituents end up locked in this eclipsed conformation. Okay, so here's our Newman projection view post-epoxidation. As we can see, it matches our model kit. And now, as you can see, these methyl groups are on opposite faces. And if we wanted to draw this in dash wedge, all we have to do is rotate it, and in turn, note the fact that the epoxide, in this case, if we're looking at it from this perspective, the epoxide is wedged, pointing towards us. The other perspective that we can use is the front-on perspective. In this case, the methyl group on the left is wedged. The methyl group on the right is dashed. This methyl group's pointing towards us. This methyl group's pointing away from us. So there are many ways that you can draw the stereochemistry for these alkene addition reactions. And as you can see, if you use a model kit or if you use the Newman projection view, it can make this process a little more efficient. Let's take a look at what happens for the Z alkene. So again, we're going to start from our Newman projection view. Both the methyl groups are on the same side of the alkene. Allow me one moment. From here, we're going to form the two carbon-oxygen bonds in our epoxide. Remember, the epoxidation, the carbon-oxygen bonds are formed syn to one another. And as a result, we get the following net stereochemical outcome. In this case, the two methyl groups are on the same face. So for example, if we were drawing it from the side-on perspective, both the methyl groups would be wedged, while both of the hydrogens would be dashed. So as you can see, the Newman projection view is another way to approach these alkene addition reactions. And you may see me use this Newman projection view throughout some of the lectures and exam discussions. It's just another way of visualizing these reactions. So to make sure that we're comfortable with predicting the outcome of alkene addition reactions, let's take a look at the following reaction, and I'd like you to predict the products. So pause the video at this time and work through this example, and then we'll discuss. You may want to make a model, or you can use the Newman projection view, whatever you prefer. So in this case, we have chloroform and sodium hydroxide. These are textbook conditions to make the dichlorocarbene. So in this case, we end up with abstraction of a proton, followed by loss of chloride, and that in turn gives us the dichlorocarbene, which engages in a concerted cyclopropanation reaction, except this time, instead of making a cyclopropane, we're making the dichlorocyclopropane. So in this case, starting from the Newman projection view, we have a Z alkene. These methyl groups are cis. So in our Newman projection view, the methyl groups are on the same side. We are forming two carbon-carbon bonds syn to one another, and that in turn yields the following Newman projection view. This is equivalent to saying that both of these methyl groups are on the same face. So if we had our dichlorocarbene, and this reaction finishes and we get the dichlorocyclopropane, this is equivalent to saying you have both of the methyl groups wedged on the same face, while both of the hydrogens are dashed. This is one of the benefits of the Newman projection view. It is pretty efficient at allowing you to visualize the stereochemical outcome of alkene addition reactions. Let's now talk about another reaction pathway concerning concerted addition reactions. So concerted alkene addition reactions occur as the name implies, via a concerted mechanism. And these concerted alkene addition reactions yield the syn stereochemical outcome. So I'm going to make a model of the following alkene. And the reason this alkene is more highly substituted is in part because many of the reactions that involve the concerted pathway are relatively sensitive to substitution, and they in turn will yield preferentially the Markovnikov or anti-Markovnikov regiochemical product. One concerted alkene addition reaction that's quite common is hydroboration oxidation. In this case, hydroboration oxidation prefers to install the boron, and implicitly thus the oxygen atom, at the least substituted position, giving the anti-Markovnikov product. So the reason why we look at substituted alkenes is to in part highlight the regiochemistry of some of these reactions. So with that prelude in mind, here is our model kit. Here is the model of this E-alkene. It's an E-alkene because the highest priority substituents, the ethyl group and the methyl group, are on opposite sides of the alkene. They're trans to one another. So in hydroboration oxidation, the hydrogen and the boron atom are installed on the same base. So if we're looking at the hydroboration oxidation reaction, we have our hydrogen and boron atom. The hydrogen and boron atom both are installed on the same face, in part because the carbon-boron bond formation occurs concomitantly with carbon-hydrogen bond formation. The boron is donating a hydride equivalent to the alkene. So, importantly, where the boron is installed is not arbitrary. Remember hydroboration oxidation? The hydrogen and boron are installed syn, and the boron is installed on the least substituted position, which is the carbon on the left. So if we install the boron and hydrogen atom, of course, after oxidation, because the oxidation preserves stereochemistry, after the second oxidation step, net, we install an alcohol and hydrogen syn to one another with the alcohol on the less substituted position. Now, let's remake this model, except in our model kit, let's make sure that we have just a normal single bond between the carbon substituents. And this is going to make our lives a lot easier if we want to do any bond rotation. So here's the product after addition. We could draw this as is, but I want to show you what happens if we do some bond rotations. So to this end, let's make a single bond model of this structure. So I have this structure on screen for you. I'd like you to make a model, just making sure that there's a single bond between your two central carbons. And I will show you the completed model momentarily. Okay, so here's our completed model. So as you can see, we still have all of our methyl and ethyl groups in the right spot. As you notice, the alcohol and hydrogen are syn to one another. Now, if we wanted to draw this in a dash wedge depiction, you could just draw it saying that, okay, this alcohol and hydrogen are pointing towards us. This hydrogen and methyl group are pointing away from us. So we'll draw one moment. So we'll draw our two methyl groups just flat, drawn with a normal line. The alcohol and hydrogen are pointing towards us, so they're wedged. This hydrogen and ethyl group are pointing away from us, so they're dashed. We could do that. That's one depiction. Let's look at another depiction. And to do this, we just have to do a little bit of rotation here. We'll just change our perspective a little bit. Just one moment. So what we're going to do is we're going to adjust our perspective. And let's just take a look at this molecule. So in our original perspective, we had these two methyl groups drawn flat. This alcohol and hydrogen are wedged. This hydrogen and ethyl group are dashed. And this is a perfectly valid depiction. Another perspective, and one that you can think about a little bit, is this kind of side-on perspective. The only change, really, in this side-on perspective is that because we've rotated our molecule, what we now see is that if we keep this the longest chain, and we keep this longest chain completely flat, then what we see is this alcohol is still wedged, this hydrogen is still wedged, but now the methyl group is dashed. So this is another depiction. So the hydrogen is wedged, the methyl group is dashed. In effect, we've just taken this bond and rotated it. Just to prove that this is rotation and that the overall stereochemistry has been preserved, this stereocenter is R and R. This stereocenter is R here, and in the product, it is also R. So we haven't changed anything in terms of our overall stereochemistry. We've just drawn a different perspective for this molecule. Okay, so let's take a look at what happens for the Z alkene now. So let's break out our model kit once again. And let's go back to our original model. So here is the model for the Z alkene. In hydroboration oxidation, the net result is the boron and hydrogen are installed syn, and thus the alcohol and hydrogen end up syn in the final product. The alcohol, which is derived from the boron atom, is installed at the least substituted position. So if we install the alcohol and hydrogen atom with the alcohol at the least substituted position, we get the following product. Now, let's make our normal model of this compound. And let's set it up so we have a carbon-carbon bond between the central carbons, so we can do some bond rotation. Here is our adjusted model of this compound. And as we can see, in this case, now, if we look at it from this perspective, we see the alcohol and hydrogen are wedged, but now the hydrogen and the methyl group, instead of the ethyl group, are dashed. So let's draw that depiction. So we have our alcohol and hydrogen, which are wedged, pointing towards us, and the hydrogen and methyl group are dashed. As we can see, the main thing that is changed is this stereocenter here, which, as we can see, now has the opposite configuration. This stereocenter is now an S stereocenter. It has the opposite configuration. We have a different arrangement of substituents in 3D space in our product. The reason for that is because if we look at our reactants, because these are two different alkene stereochemistries, we get two different product stereochemistries. This is a hallmark of stereospecific reactions. The stereochemistry of your product depends on the stereochemistry of your reactant. Okay, let's look at a rotated perspective. So let's take our model, and in this case, we already sort of have the longest chain, but if we wanted to draw this in the same perspective that we had our original, would look something like this. Whoops, other way. There we go. And now, as we can see, the alcohol is still wedged, but this time the methyl group is wedged. The methyl group is pointing towards us. So the alcohol and methyl group are pointing towards us in this depiction. And as we can see, if we look at these two views for these two different products, what we see is that if we change the alkene stereochemistry, we in turn change the product stereochemistry. So this is one way of looking at alkene addition reactions. Let's try to approach this now from the Newman projection perspective. So let's take a look at this same hydroboration oxidation reaction, but this time from the Newman projection perspective. So I'm going to make the E alkene and get that set up. And then we'll take a look at what this model looks like from the Newman projection view. Okay, so here is the E-alkene. As you can see, the ethyl and methyl group are trans to one another. They're on opposite faces. If we look down this carbon-carbon bond, we see the methyl groups are both on the right, the ethyl groups on the left. Let's draw that. Okay, so in hydroboration oxidation, both the hydrogen and boron atom are installed syn to one another, with the boron atom being installed on the least substituted position. So the boron atom's installed on our front carbon, the hydrogen atom is installed on the back carbon. That in turn yields the following Newman projection perspective. Now, of course, the boron after the oxidation step is going to be replaced with the alcohol. So I'm going to draw the alcohol in place of the boron atom. Let's show this from the model kit perspective. So the alcohol is installed at the least substituted position. The hydrogen is installed at the most substituted position, and that yields the following product, which from the Newman projection view has the methyl groups on the right, the hydrogen and ethyl group on the left, and the alcohol and hydrogen pointing up. Now, if we look at this from the side-on perspective, before we do that, we're once again going to make a normal model depiction. Just so we can do some carbon-carbon bond rotations. So here's our normal model for this hydroboration oxidation product. And as we can see in this case, if the, oops, one moment, if the two methyl groups are drawn flat, the alcohol and hydrogen are wedged, while the hydrogen and ethyl group are dashed. That also makes sense if you think about it looking at it from this perspective. The methyl groups are in front, while the hydrogen and ethyl group are in the back. So the Newman projection view is quite useful for visualizing the outcome of alkene addition reactions, and it's just another tool that you can employ. Let's try now and let's take a look at the Z alkene. In this case, the methyl and ethyl groups are on the same face. They're on the same side. They're both going to be on the right, while the hydrogen and back methyl group are on the left. One thing I like about the Newman projection view is it lets you do a lot of manipulations like using a model kit without necessarily having to have the physical model kit in front of you. I encourage you to use the model kit, but it's important to develop a way to visualize molecules and be able to approach molecular shape using pen and paper in addition to a model kit. Okay, so in this case, the alcohol is installed net on the least substituted position. The hydrogen is installed in the most substituted position. This is the regiochemical outcome of hydroboration oxidation, and that in turn yields the following Newman projection view. where both the alcohol and installed hydrogen are on the same face, same side, they're installed syn to one another. But because the starting alkene stereochemistry is different, our product stereochemistry is different. Now, the methyl and ethyl groups are syn to one another. The alcohol and hydrogen are still wedged, but now this methyl group and hydrogen are dashed. To show you what this looks like, here's the methyl and ethyl group. Here's the alcohol, here's the hydrogen, and now in the back, we have this hydrogen and the methyl group. So as you can see, the stereochemistry has changed because our starting material stereochemistry has changed. Now, one thing I'd also like to note, because we looked at both an E and Z alkene, this general scheme can be generalized to any alkene you encounter. You just have to properly label the substituents and note the relationship between substituents. Because we looked at the reaction pathway for an E and Z alkene, this general scheme applies to any E and Z alkene. So that's in part why we look at an E and Z alkene for all of these examples. Okay, just to make sure that you're following along with predicting the stereochemical outcome of these reactions, other types of concerted alkene reactions that yield syn addition products include hydroboration, hydrogenation, and dihydroxylation. With hydrogenation being a little bit less, you often won't see the stereochemical outcome of hydrogenation in a ton of detail unless you're dealing with a polysubstituted or tetrasubstituted alkene. Oftentimes, because if you install hydrogen and there's already a hydrogen in place, that's no longer a stereocenter. At least you're not generating a pair of diastereomers anymore. You're generating a pair of enantiomers. Point aside, these are the three major types of concerted alkene addition reactions that you'll encounter. And to test and to make sure that you're comfortable predicting the products of these alkene addition reactions, let's take a look at the dihydroxylation of the following alkene. So pause the video, work through this example, and then we'll discuss. Okay, so first and foremost, this is an E alkene. Under dihydroxylation conditions, the two hydroxyl groups are installed syn to one another because the first step involves formation of the osmate ester. So let's show this initial schematic. Okay, so dihydroxylation occurs with a syn stereochemical outcome. So let's make a Newman projection view. We have the two methyl groups syn to one another. They're on the same face. Well, they're cis to one another because this is an alkene. They will be syn to one another in the product. So both the methyl groups are on the right. The hydrogen and ethyl group end up on the left. Okay. The two alcohol groups are installed syn to one another. And that in turn gives us the following Newman projection view. From here, we see that if the two alcohols are syn, they're both wedged, the hydrogen and ethyl group must be dashed. So we draw out our alcohols wedged, and the hydrogen and ethyl group are dashed. That in turn gives us the predicted product for this alkene addition reaction. Wonderful. So let's look at now the last class of alkene addition reactions, which are ring opening reactions, which yield anti-products. So in this pathway, you're going to form a ring initially, and then the ring is opened by a nucleophile to give an anti-product. A classic example of this type of reaction is bromohydrin formation, where you make the cyclic bromonium ion intermediate, and then it gets opened up by water. So let's take a look at this reaction. So here's our model. We have our textbook E-alkene, and we have the model that we've been using throughout this discussion. Now, in the first step, you're going to form a bromonium ion. So you have a Br plus equivalent. You end up with cyclization to yield a bromonium ion. Here's what this bromonium ion looks like. So the bromonium ion is installed syn. So it looks a little bit like this. As we can see in the model view, the hydrogen and ethyl group are in the back. They're dashed. Now, this bromonium ion is going to be opened up by a nucleophile, in this case, water for bromohydrin formation. Water is going to attack from the opposite side because it's an SN2-like process, and water is going to attack at the most substituted position, which is on the right, because it's the position most able to stabilize a positive charge. This carbon-bromine bond is also weaker as a result of this carbon being able to accommodate more cationic character. So water attacks anti to the bromonium ion because it's SN2-like, we're attacking the sigma star. This breaks the carbon-bromine bond, and this yields the anti-addition product. Let's make a model of this compound. Let's make a model of this compound because we're going to do some manipulation, some carbon-carbon bond rotation to help us better visualize and help us better understand what is happening in this reaction. So let's make a model with our normal single bond between our central carbons so we can do some carbon-carbon bond rotation. Often these anti-addition products are the hardest for students to properly visualize. So this is why we're going to show this model and how we can rotate it. Okay, so in a rudimentary sense, if we have this double bond model, we can see, let's look at it from the single bond model perspective. So here's our single bond model perspective. Here we go. As we can see, the two methyl groups are on the same side. The bromine and oxygen atom are on opposite faces. They're anti to one another. So if we look at this from the side-on perspective, we see that the bromine is wedged, the alcohol is dashed, and the methyl group is wedged. So the bromine and methyl group are on the same face, while the hydrogen and alcohol are on opposite faces. So we drew ring opening. We ended up with the following depiction. And this is equivalent, looking at our model kit, to this flat view where the bromine and the methyl group are wedged, while the hydrogen and alcohol are dashed, as we can see from this model. So here is our original view. And as we can see in this original view, the bromine and the alcohol are on opposite faces. And if we look at it with the methyl and ethyl groups flat, the bromine and methyl group are wedged. They're pointing towards us. Let's repeat this process, this time with the Z alkene. So again, we're going to make a model of our Z alkene. So here's the Z alkene. The methyl and ethyl group are cis to one another. We're going to form our bromonium ion. And that yields the following bromonium ion, with this time the methyl and ethyl group still cis to one another. As you can see, when you change the reactant stereochemistry, your product stereochemistry changes. Now, water is still going to attack and open up the bromonium ion from the opposite side at the most substituted position. Here's what that looks like using our model kit. So we're going to attack opposite to the bromonium ion. We're going to open the bromonium ion at the most substituted position. This yields the net anti-addition product. So that looks in a rudimentary view like this. Let's now break out our single bond model. So let's make a single bond model of the following structure. And this lets us do some carbon-carbon bond rotation, gives us a little bit more freedom to deal with this structure appropriately. So here is our single bond model. As we can see, the methyl and ethyl group are syn to one another. The bromine and oxygen atom are anti to one another. They're on opposite faces. So we could draw this molecule like so and call it a day. But let's try to rotate it so that our view is the same as in our prior example. So I rotated it so that our straight 5-carbon chain looks the same as in our initial prior view for the E-alkene. And as we can see, this makes really clear the difference in stereochemical outcome. Because now, in this case, the bromine and alcohol in this view are both wedged, while the methyl and hydrogen are dashed. So just to show what we did here, here is our initial view. And we could draw that. So let's just draw that. So in this case, the bromine and methyl group are wedged, the hydrogen and alcohol are dashed. But this is equivalent to, if we rotate our carbon-carbon bonds, the following model. And this really drives home the point. If we take a look at this molecule drawn exactly the same way as our E-alkene product, what we can see very clearly is if we have two different alkene stereochemistries, our product stereochemistries will be different. You start with a pair of diastereomeric alkenes, you end up with a pair of unique and well-defined diastereomeric alkene addition products. Okay, so we've done this exercise with a model kit. Let's now try to visualize this reaction looking at the Newman projection perspective. So in the Newman projection perspective, for this E-alkene, the two methyl groups are cis to one another. They're on the same side of the alkene, while the hydrogen and ethyl group are also on the same side, except they're on the left. Methyl group's on the right, the hydrogen and ethyl group on the left. we are going to form our bromonium ion, syn, and that in turn yields the following Newman projection view for the bromonium ion. Let's show this using a model kit. So here is our initial alkene. It's an E-alkene because the high priority groups are on opposite sides. If we look at our Newman projection view, both the methyl groups are on the right, the hydrogen ethyl is on the left. We form the bromonium ion. The bromonium ion is formed on the same face. And as you can see from our Newman projection view, the methyl groups are on the same side, the hydrogen and ethyl groups on the same side. Next, we're going to open up the bromonium ion by attacking at the most substituted carbon, which in this case is going to be the back carbon. This is going to open up the bromonium ion like so, and this yields our final Newman projection view. So looking at our Newman projection view, the bromine is up, the hydrogen is down, the methyl groups are on the same side, the hydrogen and ethyl group are on the same side. So let's draw that. So water attacks the most substituted carbon and opens up the bromonium ion. This in turn yields the following Newman projection view. And from here, there are many ways that we can take this. Oops, that should be an ethyl group. But the easiest way from the Newman projection view is to just draw these methyl groups flat. We see that so let's take a look at it from the model perspective, just to help us bridge this gap. So here is the ring opened anti-addition product. Let's take a look at it from the perspective of our single bond model. So I'm going to make a single bond model of this structure. Okay, so here is our single bond model. Here is the Newman projection view. As we see, the methyl groups are on the same side. The bromine and alcohol are pointing in opposite directions. The bromine's up, the alcohol's down, and the ethyl group and hydrogen are on the left on the same side. Now, if we just rotate our Newman projection view, we see that after rotation, the bromine and the methyl group are wedged, while the hydrogen and alcohol are dashed. So this in turn can be seen as well by thinking about, if we look at the model from this perspective, this bromine in the front and this methyl group in the back are wedged, they're pointing towards us, while the hydrogen and alcohols are behind the model kit view, so they're dashed, they're pointing away from us. So this gives us the following view, where the bromine and methyl group are wedged, while the hydrogen and alcohol are dashed. As we can see in the model. Okay, let's look at the Z-alkene. So the only thing that changes for the Z-alkene is that in the Newman projection view, now the methyl and ethyl group are cis to one another. So now the ethyl group is on the right. Everything else stays the same. The bromonium ion still forms and still forms syn. From here now, the bromonium ion is opened up by water. That in turn yields the following ring open Newman projection, except this time the methyl and ethyl group are now cis to one another. So the only thing that changes here is that the second stereocenter now has the opposite configuration. What that means is this bromine and ethyl group are now both wedged. While the alcohol and hydrogen are still dashed. This structure is equivalent, as we demonstrated in the prior example, to the following depiction. The reason why I'm showing you this is because it's really important to be careful when you rotate your carbon-carbon bonds that you retain the stereochemistry of the product that you started with. Just because the stereochemical outcome of an alkene addition reaction means that the bromine and alcohol are installed anti to one another, that doesn't mean after you rotate your bonds or change your view and perspective of the molecule that the bromine will always be dashed and the alcohol will always be wedged. It's important to note that you need to draw out each step of the reaction, draw the product from each step, and then from there you can rotate your carbon-carbon bonds to get the desired view. Okay, so just to make sure we're comfortable with this, let's try to predict the product of the following ring opening reaction. Common classes of ring opening reactions that yield the anti-products include oxymercuration, bromohydrin formation, and epoxide opening under both acidic and basic conditions. So take a look at the following reaction, pause the video and work through this example, and then we will discuss. Okay, so in this case, we have a Z-alkene. In the first step, we're going to generate an epoxide. So let's start with our Newman projection view. We have the methyl group on the right, hydrogen on the left. The ethyl group is on the right, the methyl group is on the left. In the first step, we're going to form an epoxide. So the oxygen atom is installed syn. This gives us the following Newman projection view, whereas we can see the methyl and ethyl groups are syn to one another. From here, under acidic conditions, water will attack and open up the protonated epoxide at the most substituted carbon. This yields the anti-diol. So as we can see, if we keep these methyl groups in the plane of the page, we see that the alcohol and ethyl group are wedged, while this hydrogen and other alcohol are dashed. This in turn gives us the following view, where we have the alcohol and ethyl group wedged, while the hydrogen and the second alcohol are dashed. Wonderful. So this concludes our overview of our alkene addition reactions, and this concludes our Chapter 7 Supplemental Model Kit Exercise Lecture.